tensile, so it's pushing away, right? So from the material, it's pulling away. This is in tensile. So this is how you draw your stress profile of the cross-sectional view in the x direction. Okay, and what you can see over here at the neutral axis, right? So this is the location of the neutral axis. We realize that stress x is also equal to 0. Okay, so this is how you sketch. I believe this is just a recall on with your 2P, right? In 2P, I believe Dr. Koshi will have taught you how to draw a stress profile, the cross-sectional view stress profile, and define what is a neutral axis. So far, any questions, please? No? Good. Now, today I realized that our lecture is only up to 11:20. I don't have tutorial today, but do you mind if I proceed the tutorial I teach until 12 o'clock, please? Do you mind me doing that? Anyone, please? That I will proceed to 12 o'clock. I'm looking at anyone typing anything. No one is scolding me now. Even I have sure. Okay. Right. If you have, just type. Okay. I want feedback from you. Okay. Right. Okay. So we go until 12. So the next thing that I like to highlight. So what we have done down here based on the agenda objective. So you guys now know the basic theory of pure bending. So the next one is what is similar by simply supported beam and cantilever beam. Okay, I want especially when we go into pure bending. Okay, so we know. Okay, so I'm going to write down here. We're going to address the issue between the difference between or the similar, not the difference, cheeky. So the similar characteristic between simply supported and cantilever beam. And I want to highlight for you down here, this is a typical example on failure analysis. Okay, this is a typical example on failure analysis. Okay, so I'm going to draw a simply supported beam. So we are going to deal with a point load first. Okay, so we have our structure over here. Right, same structure that we have, simply supported. Right. I have a load P coming down here. A point A. We have our point B. I want to use the same what we have. Yep, point B. And point C. And this is exactly with a specific distance. And this is our L/2. Now, can anyone tell me where the structure will fail? Anyone, please? Anyone? I know I'm not able to see the chat. Okay, anyone?
At B, the structure.
Right. Well done. At point B. Okay. At point B is where the structure will fail. So structure will fail at point B. Now, this is very important. Okay. So whatever analysis that we do, all analysis will be calculating stresses at point B. Okay. So point B is where we want to calculate our stresses, right? Why at point B? Because it's going to fail. We are not going to care about point A, and we are not going to care about point C because it's not going to fail there. Okay. I have supervised a lot of PhD students, male and female. Okay. I'm not being sexist down here, but female students are very efficient. They don't waste time. Okay. They will calculate exactly where it will fail. Okay. Whereas male like me, I will do a bit of bullshit, okay? I will calculate point A, I will calculate point C, and it's pointless. Be very specific. That's why if you want to have an honest opinion, find a female or a girl or a woman to tell you, and they'll be real straightforward. Men, we are very political, okay? Oh, I don't want to piss him off. No, okay? You want, so coming back to here, we want to calculate stresses at point B. Okay, now I'm going to draw a cantilever beam now. Okay, I'm going to draw. So we know that structure will fail at point B. Okay, then I would like to draw a cantilever beam now. Okay, so I'm going to construct a cantilever beam. I'm just going to look at half of it. Right? So it's just half of it over here. This is point A, and this is my point B, right? And then I have a force down here, and the force down here is at P/2. Okay, and then the distance from here to here is L/2. Okay. Now, question for you all now. With a cantilever beam, where will it fail? If you look at a cantilever beam, anyone?
Would it fail in between A and B? Because it would have like a bending towards B a little.
So you are thinking that it will fail somewhere around here, right?
Yeah.
Right.
Will
So
it fail at B?
it'll be at where? Someone say
At
something.
B?
At B. Why? I'm not saying that you're wrong. I'm asking you why. Hello.
Sorry, I didn't hear you there. Would it not like snap off? Oh wait, we're only looking at half. Sorry, never mind.
No, you're right. Don't say never mind. Okay. At B is where it will fail. So structure will fail at B. Okay. Now, why is that at B then? Because at a cantilever beam, for a cantilever beam, right, your bending, your moment will be maximum at point where? At point B. Okay. Now, hey, don't take my word for it. Why not you do an experiment? Okay. Why not? You carry out an experiment right? You carry out an experiment on your own to see where it will fail. Okay, so if you were to take a ruler, hold on guys, hold on. So if you were to take a ruler, okay, I'm going to do something that I've not done before. Okay, I'm going to, right, so can you all see me now? Yes or no? No answer.
Yes.
Okay. So this is, good morning. So if I were to bend my ruler, right, well, I'll bend my ruler hard enough. I'm not going to break it, okay, you cheeky sort. It will break at the center, yes or no? Right, your break where my forehead is now, or my nose is touching now, you'll break at the center. If it's a cantilever beam, if I bend here now, it will break at my finger, yes or no? Right? It's not going to break at the free end. It's not going to break at the free end, right? It's going to break where I'm restricting what? Motion over here for a cantilever beam. Okay, this is because we have a maximum moment, counter moment reacting on our structure. Okay, so I'm going to share my screen again. Right. So what you see now, are you all looking at my OneNote screen now?
Yes.
Okay, I want to be sure I don't. Okay, so we know that they were failed at point B. Okay, so what I'm going to do now is we're going to prove mathematically why this is the fact. Okay, and why when a simpler supported beam, this is like equivalent, okay, to a cantilever beam. Why a simpler supported beam, given at the loading that we have seen, is equivalent to a cantilever beam. Okay, so we are going to first look at simply supported first. Okay, so if we were to draw, or we are going to do our shear force diagram and bending moment diagram. So we're going to form equations now. Okay, so we are going to look at stress at a limit of 0, x, and L over 2. Okay, so I'm going to draw my free body diagram. So this is our point A. And over here, we have a reaction force, which is P over 2. And then this distance is X, right? So we want to form, we want to find out what is happening at point X. And this is the shear force as a function of X. And over here, or this is exactly where we are looking at, okay, now. And that is moment as a function of X. Now, anyone have any idea why that direction? Anyone, please? Why at X distance, the shear force is going down and the bending moment is going anti-clockwise?
Isn't it supposed to be the reaction to the force applied? That's why it's like downwards, or because P over 2 is upwards.
No, I thought it was also when I was your age, but later on I found it was not. Anyone else, please? Thank you. Good try, okay? Because I had the same mind of thought also. Anyone else, please?
I know if the shear rotates the object clockwise, it's considered positive. I don't know why.
Okay, so probably you guys have forget. You guys have learned this in 2PO4. This is because we assume positive shear. Okay, we assume positive shear. And positive bending moment. Okay, that is why the direction is so if our analysis, so this direction is when we analyze left to right. Okay, so we analyze, so this is our left, and then it's going towards the what? The right. So that's why that orientation. Later on, I'll help you recap when we go into shear force and bending moment diagrams more. Okay, so now, so from here we are going to do static analysis.